So I'm not going to make a big deal about the first of the two options. It's called cylindrical coordinates. And it shouldn't surprise you that it's based on the geometry of cylinders. So cylinders are based on circles together with vertical lines. So it's not too surprising that we're going to use polar coordinates in the plane, and then just plain old z in the z direction. So it's just like doing what we're used to, where you set up iterated integrals in some sort of order where you think about z on the inside, and you say for each fixed point in the region in the xy plane, you figure out what z does here. Well, the only difference now is we're going to replace the dy dx by r dr d theta. And we're going to do exactly set the region up in the xy plane by setting it up in polar coordinates, and then do what z does. Okay?
And Houdini says you can flip those around at will.
You can flip as you wish, but this is the canonical order that I'm going to suggest you always set it up in. Put z on the inside, and then do polar as we've been doing with the theta on the outside, and r often depending on theta. Okay? So this is not that difficult, but let's set up a couple problems. I mean, generally, as you guys have already experienced doing your homework, the hard part is getting an idea of what the region looks like and on how to project it into the appropriate two-dimensional plane. And then after that, it's usually pretty easy. So let's do this. Let's say set up iterated integrals. To compute, let's say, the integral of z dv over omega, where omega is the region bounded above by the sphere x squared plus y squared plus z squared equals, I don't know. I'll fill this in a minute. And bounded below by the paraboloid x squared plus y squared equals z. So I'm going to make the sphere have a strange radius, square root of 6. We'll see how it comes out.
I like this.
Okay, so draw yourself a sketch of the picture. What does it look like?
Well, you guys are of a parabola.
Okay, so I've got a sphere of some radius centered at the origin.
Wait, is the sphere centered at the origin?
Yes, the sphere is centered at the origin.
Oh yeah, centered at the origin.
So I have an upward-facing paraboloid that goes something like this. And so you get the region that looks like somewhat like a strange-shaped bullet or something. Not that I would know. Okay, so this is omega in here. So do you convince you? So notice you have symmetry about the z-axis.
Yeah.
That makes cylindrical coordinates seem like the natural coordinate system to use. Okay, because you're going to have theta symmetry, right? The fact that it's symmetric about the z-axis means the geometry does not depend on theta, and so this is a very natural coordinate system. So note symmetry about the z-axis actually recommends cylindrical coordinates. All right, so tell me what to write down.
function?
So I want to write down an integral. I'm integrating a continuous function, so Fabini says I can write it as an iterated integral and I don't have to worry about it. What shall I put here?
Z.
Okay. Do you guys want us to keep the r here, or probably we should move it out in front with the function, right? So let's put the r there. So there's, this part is our dv. What's the function in cylindrical coordinates?
Z.
Z. Didn't have to change that. All right. So do our standard thing here. Figure out what the projection of this would be into the xy plane, and then figure out what that is in polar. So what is the projection of that region? Say it correctly. No. Circle's a curve.
Disk.
Thank you. It's a disk that you get by projecting the fattest part, which is where the two things intersect.
Which is Z. Or no,
So do we agree that the region in the xy plane is that? So what's the radius? So theta is obviously, as I said already, going from 0 to 2 pi. Now what's the radius of this disk? How do we find that?
solve for Z and go back.
You could solve for the z here, or you could solve... So what should I do with these equations if I want to work in cylindrical coordinates?
Put an R.
So the paraboloid is z equals,
R squared.
and the sphere is?
R squared plus Z.
Good. Okay, and Cameron's suggesting that it would be easier to just put in z for the r squared, get an equation for z, and then go back and figure out what r is. Or we could substitute z equals r squared and we get a quadratic in r squared. Same difference. Right? So you solve and you get what? Z squared plus z minus 6 equals 0. Z minus 2 times z plus 3 equals 0. Is that correct?
So now it's not -3.
So z equals 2 or z equals -3. I'm not feeling the minus 3. Agreed? Don't think you can have a negative number be a square number, unless we're working with complex numbers. All right, so this is z equals 2 here. What does that tell me the radius of that ball or disk in the xy plane is?
Square root
Square root 2. So this guy has radius square root of 2. So r goes from 0 to square root 2. Is there a question?
I was
So we've decided that this is happening at z equals 2, so r squared then is 2. Right, so
right, that R, okay, yeah.
okay. All right, now comes the easy part. You say to yourself, for an arbitrary point in that region in the plane, what does z do? It enters and it exits. It enters where?
X squared plus y squared.
At the paraboloid,
Which is r squared.
which is r squared. And it exits. It exits at the sphere, and so you solve for z for the sphere equation. 6 minus r squared. Square root.
Don't we know that?
Mm-hmm.
Alright, never mind.
Okay.
Yeah.
Just as a really easy problem, but we're going to actually use this. It actually represents something interesting physically, as you'll find out on Friday. let's take a cylinder and ask, what is the integral of the square of the distance from the axis of symmetry of the cylinder? Follow that? Cylinder. Filled in. So take a solid cylinder. And by that I mean a right circular cylinder. Do I have to write that all out? Okay, I didn't. Radius A, height H. And what I'm interested in, and presumably the people in here who've taken physics know why I'm interested in this, but the rest of you will find out Friday, I'm interested in taking the axis of symmetry and asking what's the integral over the region of the square of the distance from the axis over the region, dV. How many people recognize what we're doing? Come on, Michael! All right, so how should I stick this in? Is it?
Square the distance from the axis, and you squared it.
Oops! Thank you. I forgot I did the square of. Thank you. So, how shall I set up my cylinder in 3 space to have the most convenient coordinates here?
You want the center, you want the axis to be the z-axis.
Yeah, let's make the axis be the z-axis. And let's put the base of the cylinder at the xy plane and go up a height h. How's that? So what am I actually doing here? I'm integrating what is the square of the, if I take a point here, what's the square of its distance to the z-axis?
X squared.
X squared plus y squared,
R squared.
which will turn into r squared in a second. So I'm interested in integrating the square of the distance, x squared plus y squared, square of the distance, comma. And then I'm going to put it in cylindrical. This, as you guys have said, becomes,
R squared.
and then I multiply by,
R.
so I have r cubed. Limits, please. Theta goes,
0 to 5.
r goes 0 to a, z for any fixed point in the, that's sort of boring, right? 0 to h. And pretty much you can do this problem in your head. 2 pi h a to the 4th over 4. Agreed? Right, then go dz is h, then I integrate r cubed from 0 to a, I get a to the 4th over 4. So I have pi over 2, and I'm actually going to write it this way for reasons that you will see on Friday. I'm going to take the volume, which is pi squared h, factor it out, and what's left?
A squared over 2.
A squared over 2. So you will see this sort of thing happening a few more times today and more on Friday. Okay. You'll find out.
I probably won't though. What is it?
Hmm?
I probably won't though. What is it?
What do you mean you won't?
Physics application?
I'm going to do it on Friday.
Oh.
All right. So we're going to do a few more examples in cylindrical coordinates, but I want to actually do spherical coordinates, and then we'll do examples both. And you'll have web work where you have a couple problems where you have to set up in both just for practice. So spherical coordinates. These are the coordinates that you would use if you lived on the surface of the globe. So if you live on the surface of the globe, you don't think about r, theta, and z.
What do you mean like don't we live on the surface of the globe?
Latitude and longitude is what I'm after here. So, however, we're not going to use literally latitude. We're going to use a slightly distorted version of latitude. So, we will take a point on a sphere and talk about what the radius of the sphere is. So that's going to be one of my coordinates in 3 dimensions. We'll call that rho. Physics books call it r, just to confuse you.
Who's right?
I'm right. Physicists don't like rho because they want that to be density. I'm going to use delta for density because I'm already using rho the way math people use it. So rho is the distance, it's the 3-dimensional analog of r in 2 dimensions. It's the distance from the origin. You're then going to measure the angle from due north. And we're going to call that phi. Physics books call that theta. You're then going to say, oh, well, we still have theta. If I project my point down to the xy plane, I can measure the angle in the usual polar coordinates way from the positive x-axis, and that's theta. The physicists call that phi. My view is, you guys are used to polar coordinates. I want to keep polar coordinates as polar coordinates and not mess you up. So in our polar coordinates picture, this length here would be r, right? The distance from the origin in the plane is r. So I could actually make myself a nice little right triangle here and put r here, just to help me. So phi, so rho, again, customarily is going to go only from 0 up. It literally means distance. Phi is only going to go between 0 and pi. So phi is what you would normally think of as being related to latitude, but it's not quite. Right. But as you go along this half great circle here, fixing theta and varying phi, you move along that half circle, which is called a line of longitude.
It's the long way.
It is, or because you're specifying a fixed theta, and that's the longitude. Everybody lost, or are you okay?
Is rho greater than or equal to or just greater than 0?
Well, if you actually are at the origin of 0. Now, some people are going to say, well, wait a minute, why can't phi keep on going and be bigger than pi? Yeah, so exactly what Justin just said. If you rotate yourself around that line of latitude, if you let theta go from 0 to 2 pi, it takes you to the back part. You don't need phi to do it. Fixing this phi and then using theta to spin you around, you're going to cover all the circles.
So we do let theta go from 0 to 2 pi.
We do, or from minus pi over pi to pi, or whatever. Yeah. All right. Well, so what's my spherical coordinates mapping? I've got. Sorry, rho, phi, theta. Those are my 3 coordinates. Well, let's figure out what x, y, and z are. Start with z. Here be z.
Is it rho sine theta?
I don't know. No. Look at, you got a right triangle here.
Oh, okay.
You got a right triangle.
Yeah.
And this side is rho, this side is z, and this side is r, and this angle is phi. So what's z? Rho cosine phi. Now, here's why I prefer these coordinates to the other ways, lettering them. What's r? R is rho sine phi. But then once you know what r is, you can do what we've been doing in polar. X is r cosine, and y is r sine theta. So rho sine phi cosine theta is x, rho sine phi sine theta is y, and I am done. Those are the coordinates. And honestly, you can try to memorize this, but I think it's easier to think through this picture and just figure it out. It should only take you 10 seconds. All right, so we're going to do our standard game of converting standard shapes into spherical coordinates. Just a couple of examples that you might find useful. Sphere centered at the origin. Of some radius a. What's that in spherical coordinates?
Well, theta goes from 0 to 2 pi.
I'm just asking what equation would characterize this.
Rho equals 1, or rho equals a.
Rho equals a, right? You're looking at all points whose distance from the origin is a. So it's just the analog of a circle in the xy plane centered at the origin. Well, you know where I'm headed next. What if I shift the sphere up so it's now centered on the z-axis and passing through the origin? So now if I had a sphere of radius a, what would it do?
Use the Cartesian equation.
No, don't use the Cartesian. If you imagine slicing it with a plane at any fixed theta, what are you going to see?
Circle.
A circle. So it's like what we were doing before. No matter what angle you're cutting this at, you could imagine cutting it at that angle, but you're going to have a, what kind of triangle here? Right triangle, right? And conveniently, phi is there. The radius is a, so that makes this 2a. Should look familiar, right? So what is the equation? Rho over 2a equals cosine of phi. So it's just like what we did in polar coordinates. What happens if I try to move the sphere so it's sitting, say, on the x-axis? So that picture looks absolutely horrendous. Erase that from the tape. Suppose you drew a sphere, say, sitting on the y-axis. When we did polar, we could switch x-axis and y-axis. It was easy. Do you guys have a guess what this one would be? Sine.
Rho in terms of theta.
Theta?
Yeah.
So you don't think I should just switch that to a sine phi?
No, because it won't have any x-axis.
Huh?
You switch
It
it.
should be sine, right? If theta.
It's neither.
Pi all works with minus.
Yeah, actually, so you cannot do this. See, if you have an equation that involves phi and without theta in it, it has to be rotationally symmetric, because theta varying from 0 to 2 pi makes you take whatever shape you have and go around the z-axis, right? So if you extrapolated from what we did with polar coordinates, and you took in the YZ plane this picture, and put your phi here, as we just did, you would have an equation rho equals 2a sine phi. But then you've got to take that and rotate it around the z-axis, because not having theta in there means it's rotationally symmetric. So what shape do you get when you take a circle like this and you rotate it around the z-axis?
It's a torus, maybe?
A slinky that you combine the two halves together.
I like the torus answer, but it's not quite right.
Without a hole.
It's a holeless,
Yeah.
it's an unholy torus. If you take this curve and you rotate about the z-axis, you get, so if you took the circle and moved it over here and rotated around the z-axis, you would have an actual torus. Here you're spinning around the origin there, which means no hole. So you have a surface that looks like this, and that is, as I said, you guys called it a torus with no hole, I'll call it an unholy torus.
I don't know which one's the official name for it.
It's not.
I really wish it was. What is?
There isn't one. Okay, so basically, if we want to do a problem where we want a sphere passing through the origin, we've got to set the problem up so that we center the sphere on the z-axis. Got to set it up that way. One last example that will be useful.
So what is the equation of that?
What is the equation of what? It's a horrible mess.
Okay.
Write down, as they were saying, the Cartesian equation, and put it into spherical. It's going to have a mess with phis and thetas in it. So don't do it that way. If you have a problem that you need to set up where you have a sphere sitting on the passing through the origin, change the problem so that it's this picture. Change your coordinate system to put it, the sphere centered on the z-axis, so just change the problem. I'm not going to make you do that.
Just like change the x's and y's and make them.
Right, change your coordinates so that the sphere is sitting on the z-axis. What about a plane z equals a? What's that in spherical coordinates? Do the same thing we did with polar. What's z? Rho cosine phi. So this is rho equals a over cosine phi, just like we were doing. All right, here's the fun stuff. When we switched to polar coordinates, we had to figure out what dA became. We had to say what's a little chunk of area, and I drew you pictures to show you that you got an R and a delta R and a delta phi. So here we are in rho phi theta space. And we're mapping by our mapping G. And we're getting Cartesian coordinates over here. And what I want to do is draw you a convincing picture, for which I need colors, that says if I start at a point with a certain rho and a certain phi and a certain theta, imagine I'm here. So here's rho phi theta. I won't put it there. And that's the point in xy, phi. And now imagine that you take a little change in rho, a little change in phi, and a little change in theta. What is that going to look like in this picture? So I've got a little box in rho phi theta space that looks like taking a little change in rho, a little change in phi, and a little change in theta. And that makes a 3D box if you do that, right? You'll have blues going that way, oranges going this way, and pinks or reds or whatever that is going this way. Got a little chunk of rho phi theta space. What does that map to?
Arc of the sphere that then moved out.
So,
Like a sector of the sphere.
all right, so Ken, you're saying if I change rho,
Maybe.
that moves me out
Yeah.
this
So
way.
It has thickness.
All right, we'll put some more stuff in a minute. What happens when you change phi? You're at this point and you increase phi a little bit. What does that do to you?
Move more towards this one.
It rotates it this way, right? An arc of a circle. So at this point I have myself a little parallelogram that's curvy,
You already said works with R.
but I haven't varied whom yet. Theta. So what does theta do? Well, you come down here, and if you imagine varying theta, that's going to move you on an arc of a circle here. If this is delta theta here, it's going to move you on an arc of a circle in the xy plane that has radius r, and it's going to move you laterally on an arc of a circle. So what does that do in this picture?
It's like opening the little Chinese flash.
It moves you, the perspective is a little strange, it moves you into the board, basically, when you get arcs like that. And then you've got more red ones, and more blue ones, and you've got yourself a curvilinear cube, or box. What are the dimensions of that curvilinear box? Well, the pink guy, so the blue guy is just delta rho, right? The blue guy, I already put him in there. Delta rho is this dimension. What's the pink dimension here? That came from varying whom? Phi. So we have delta phi as this angle here. What length does that give me here? On a circle, if you have an angle, delta phi, what arc length do you get?
Delta phi times the radius.
Delta phi times the radius, and the radius is rho. So this length is rho delta phi. What about the orange length? That came from this, which the perspective is messed up. I didn't draw it perfectly here.
Delta theta times rho cosine.
No. The orange length is what? It's r delta theta, right? Because this is a circle of radius r. And r is? No. Rho sine. So you've got rho sine phi times delta theta. So G takes this little box that has volume that, and it builds you a curvy box whose volume is approximately delta rho times rho delta phi times rho sine phi delta theta.
Is the squiggly because we don't have a fudge factor?
No, that is the fudge factor. I am getting the fudge factor, but so I'm doing an approximate. It's not an exact parallelepiped, right?
So it's rho squared.
So the fudge factor is going to be rho squared sine phi. So just as you programmed yourselves in polar to stick the r in, when you're doing spherical, you're going to stick in a rho squared sine phi. And again, when we get to the last section of the chapter, we'll have a more rigorous derivation of where this comes from. Right. Okay?
there a reason why we're measuring rho from the z-axis instead of from the
You mean phi?
phi from the z-axis instead of like upward?
Because it actually is, it is more natural to go from 0 to pi than, right, so latitude would be measured from the xy plane, and you would have upwards to pi over 2 and downwards to negative pi over 2. It's just a lot more convenient to come from the z-axis, because the z-axis is easier to visualize rather than saying angle from the xy plane, but it's their equivalent.
Oh.
Mm-hmm.
For the rho change in phi, for the red line, the length of the
Mhm.
red line, weren't like the red lines closer and farther from the origin be different lengths?
Correct. That's why I'm saying approximately.
Okay, so we're just assuming.
Right, it's the same thing we had in polar when we had this picture. And we had those, and I said that was r delta theta, and this one, of course, is longer. So we're doing, right, so that's why I'm saying approximately, but we will have a justification. All right, so let's set up a couple problems in spherical. Polling the audience. Everyone have their clickers? Would you naturally do this in spherical coordinates?
No.
Why?
Because I don't use anything in that.
The sphere? What could be easier than a sphere?
The parabola.
The parabola is yucky. If you try writing this equation in spherical coordinates, it's not going to be pretty. You're going to have, there's no thetas in it, but you're going to have rho being something that looks like cosine phi over sine phi. Cotangent phi. It's just not very nice, but you could do it if you had to. But there's a more serious reason you wouldn't do this in spherical coordinates. Imagine saying to yourself, what does rho do if you fix a phi and a theta?
Sometimes it goes.
Yeah, it intersects.
Sometimes it
parabola,
ends up,
sometimes.
You would have to break it up into two pieces, because if you're in the upper part, you would go until you hit the sphere. But if you got down this far, you go till you hit the parabola. So you just don't want to mess with that. Your instincts should say, stick with cylindrical for this. However, if I draw you something a little nicer, then you should be fine with it. Suppose I did omega is the volume region bounded above by a perfectly reasonable sphere. And bounded below by, what's this creature? Instead of a paraboloid, what's that?
It's a code.
It's a cone. With what angle? Yeah. So this picture, we got ourselves our sphere.
Ice cream.
Yes, it's an ice cream cone. It's not fair. You already ate lunch, the rest of us are hungry. Now you draw yourself the cone. And again, it looks generically like the picture we had earlier, but you've got the cone on the bottom, not the paraboloid. And so omega is now the region in there. And I think you'll see in a minute why this is nice in spherical coordinates. It's also nice in cylindrical. So let's set up the integral of blah dv in spherical coordinates as an integrated integral.
Was it ever much easier to use spherical than cylindrical?
Yes. If, for example, the thing you were integrating had turned into rho, for example, that would be nicer in spherical, as long as the region's reasonable. All right, so let's say to ourselves, selves. First, I need to put the dv, so without hesitation, I write
Rho squared sine.
rho squared sine phi, fudge factor. And then I will always recommend the order I've been writing, rho on the inside, theta on the outside, phi in the middle. That's the recommended order. Disobey me at your own peril. All right, theta does what? Again, you got symmetry about the z-axis. No brainer. Phi does what? Uh-oh.
0 pi over 4.
How do you know it's pi over 4?
Pi 4 is the 3 pi 4s.
No. Theta is this angle. Phi is this angle.
Oh, right.
So 0 to pi.
Is it pi over 4? Everybody agree? When Daniel said it was a pi over 4 angle here, that was what he was thinking of.
Yeah.
Right? This line, if you like, here, has slope 1. That makes this angle pi over 4. You can get it all out of the... You can get it algebraically. If you are not confident in your abilities, you can write this down in spherical coordinates. Z equals
E. Right?
rho.
A row.
I erased it, unfortunately. No, it's up there. What's Z?
Just row.
And square root of x squared plus y squared is what in terms of spherical coordinates?
Just row.
No.
Isn't it?
Rho squared, sine squared.
No, come on. What's this otherwise known as?
R.
R. And what did we say R was?
Rho sine.
So, how can this equation hold? Which is pi over 4, right? So if you don't have any geometric intuition at all, you can still do it algebraically. I'm not encouraging that, but I am saying you can do it. All right. For fixed rho, for fixed phi, fixed theta, so you fix an angle, shoot it out at some particular angle theta, fix a phi. What does rho do?
0 to 1. Or root
0 to root 2. Piece of cake. Now, just for practice, let's just do that in cylindrical quickly. What would it be? You put your fudge factor, and now theta still goes.
0.
R goes.
0 root 2.
I don't think so.
0 to
What determines the limit on R?
how wide that cone is.
The boundary
Where it
between the
intersects.
cone and the...
Yeah.
This thing, right?
Yeah.
You want that radius. So how do we find that? Just like what we did earlier.
Well, z equals r,
Z equals R.
and we have,
What's the equation of the sphere?
yeah, the equation of the sphere is x squared plus, so r squared plus z squared equals.
So what's the R where those two intersect?
1?
1, yeah.
Yeah.
Okay? You could have gotten that from geometry, by the way. Once you knew this was a pi over 4 angle, and if this is square root of 2 here, and this is pi over 4, then this has to be 1 square root of 2. Okay. And for fixed R, Z goes from what to what?
Square root of x squared plus y squared.
Polar coordinates.
R.
Z equals R.
Square root of 2 minus r squared.
Okay? See, our chalk is erasing beautifully again. Okay, last example. I want to do the integral of 1 over the square root of x squared plus y squared plus z squared over the region omega. No, we're omega is bounded below by z equals 1 and bounded above by the sphere x squared plus y squared plus z squared equals 4. And I'm having this horrible feeling that I'm doing a Weber problem for you.
Oh,
Do you think the web works in spherical or what work is it?
Better now than now.
I said some of them they will force you to do both, but otherwise you can do what you want.
Let's do
So, looking at what I want to integrate, which coordinate system would you rather use?
spherical.
It's spherical, although you don't necessarily have to. I would rather put 1 over rho than mess with square root of r squared plus z squared. And then fudge factor, rho squared sine phi, d rho, d phi, d theta. Notice how nice that is. Limits, please. Theta goes.
0 to pi.
Uh-oh, now we got to think. Z equals 1, sphere of radius 2. So the plane is halfway up. They intersect along that circle, which looks lopsided, I apologize.
X squared plus y squared equals 1.
I'm interested in, gosh, that really is too
Oh, I'm
lopsided,
looking
it's
at
driving you
the-
nuts.
Yeah.
Balance, that would have been the best graph.
Okay, so I'm interested in this angle phi, right? I'm going to be in the region when phi is between 0 and that phi. How do I figure out phi naught? You know, this is what? And this is? So what angle has cosine equal to half? 60 degrees or pi over 3. Finally, you say to yourself, fix a phi, fix a theta, what does rho do? Enters where, exits where?
It enters on the plane.
It exits on the sphere. So I'll do the hard one for you. It exits with rho is 2.
Can you do the easy ones to show off?
And enters when? 1 over cosine phi, which is secant phi. Okay. This actually isn't that bad an integral to do it. All right,
Why
so
can we cancel out the 2 rows?
sure.
Oh, yeah.
Well, not both of them. Cancel
Yeah,
one
one
of them.
of them, yeah.
Yeah. All right, so Friday we'll do more examples in the setting of actually doing some physics problems. So I'm going to do a couple days of physicsy applications.